Hello, this video is for Stat 210, handout number 10, Part A. It includes pages 1 through 12. Okay, let's go ahead and get started. The data set for this handout is included in our Google folder for handout number 10. The name of that data set is Palpal Lymph Nodes. So what handout number 10 covers is what's called the paired t-test. In our first example, we are interested in the degree of clinical agreement between two physicians. So I have Dr. A and I have Dr. B in this data set. And I have, I think it's 32 different patients. And what the doctors were asked to do is count the number of palpal lymph nodes. So Dr. A found 4 in this patient, whereas Dr. B found 1 in that patient. Patient number 3, Dr. A found 3, Dr. B found 2. So they're pretty close in the amount of agreement for that particular patient. So we are interested in the clinical agreement between Dr. A and Dr. B. So if we open that data set, we can see that we have the patient, we have the count from Dr. A, and we have the count from Dr. B. The first thing that we're going to do is compute the differences between Dr. A and Dr. B. So my goal here is to compare the data across. I want to compare that 4 to that 1, or I want to compare that 3 to the 2, all the way down. So in order to do that, I'm going to create a column of differences. So let's go ahead and do that inside a jump. Call it differences. And that is going to be computed as simply taking Dr. A minus Dr. B's count. The analysis is going to proceed with this column of differences. So again, we're going to compute the differences between the two doctors, and I did those with Dr. A minus Dr. B. In this section, you have to know how the differences were computed. That has an impact on all the interpretations that we're going to do. In here, I've taken Dr. A minus Dr. B. The next step then is just to summarize those differences. So we're going to do analyze distribution. We're going to do the analysis on the differences here. Here's the summaries that I provided in the notes. We have our graphics again, the quantiles, the summary statistics. Can create the dot plots underneath graph builder. I'm not going to show you that, but that's where those were obtained. So here's what those differences look like. I kind of snapped a line here at 0 because if that difference is equal to 0, so I'm talking about this column here, that's what we're analyzing is the difference column. If that difference is equal to 0, then Dr. A and Dr. B are the same. So for patient number 12 here, you can see that Dr. A had 1, Dr. B had 1, so that difference is 0. Patient 15 had 7 and 7. So when this difference quantity is 0, that means the two doctors have exact agreement. There's a couple of three questions here on the bottom of page 2. I'll go ahead and stop. You can hit pause on the video and try to answer those questions. The solutions will be provided in the Google folder. Okay, so let's now talk about the distribution of those differences over repeated sampling. So here what we are going to do is consider what it would look like if I were to take repeated samples from this distribution right here. This is the distribution of the differences. So what handout 10 is about is obtaining a p-value and also margin of error calculations, or 95% confidence intervals, for the average difference. So I need to know how do these values change over repeated sampling. And in particular, how does the average change over repeated sampling? For the sample that I got, my average was 2.75. But what would happen if I were to repeat this study or take another repeated sample? So if I were to take a repeated sample here, this average from sample number 1 looks like it's 2.53. So it's a little bit smaller than the 2.75 that we got. If I were to take another repeated sample, the second time through, looks like I got an average of 3.06 here. Take a third repeated sample, I get an average of 1.91. Now I can actually use StatKey to take these repeated samples. I'm not going to go out and do that in StatKey, but we can do this with StatKey. Just like we use StatKey at the beginning of the semester to understand what happens through the repeated samples, we can do that here as well. So the averages that I got, my original was 2.75, but over my repeated samples, I should get values close to 2.75. 2.53, 3.06, 1.91, 1.69, 3.34. I could do this many times and obtain many different averages. If I make a plot of those, so a plot of all of those repeated averages, this is what that distribution is going to look like. The average of this distribution is going to be the average of the original data. So these should be centered around 2.75. The amount of spread that I have in this distribution is actually called the standard error for the mean. And the standard error for the mean, how we calculate that, is to simply take the standard deviation in the original measurements and divide it by the square root of the sample size. So here that's going to be 32. If we go back up and look at the standard deviation in the original measurements, it's 2.828. Sample size is 32 here. So to compute the standard error for the mean, I would need to take 2.828 and divide it by the square root of 32. When I do that, I get 1/2. So that standard error, which is just the standard deviation in this distribution, which is the distribution of the averages over repeated samples. So how much can I expect them to vary? How much can I expect these averages to vary? Is given by that standard error quantity of 0.50. Okay, so how do we build the reference distribution when we're doing testing? So one thing that has to happen when we're doing our hypothesis testing is that we do it under a no difference situation. So I need to take my original measurements and just shift them or rescale them slightly. I want them to have a mean of 0. So when I'm building the reference distribution for doing testing, again, I need to build that under a no difference scenario. So I have to go through this rescaling step. It's quite a simple step. All I need to do is take each observation and subtract 2.75. These data points right here are going to have an average of 0. Because I know that these, before I did the rescaling, had an average of 2.75. So just that simple subtract the average from every observation is going to have, or that rescaling will give me a situation of no difference. And now I do the repeated sampling here from this distribution. That's how I'm going to compute my p-value, is I'm going to take repeated samples from this distribution, again, compute the average of every single step, and then just repeat that many times. So at the bottom of page 4 there is what we would call the sampling distribution for the average, adjusted to have no difference. And again, that's just being rescaled. Once I have that distribution, all I need to do is figure out to what degree is my observed average of 2.75 extreme. So to compute the p-value, all I need to do here is compute the dots that are as extreme or more extreme than my observed outcome. which here my observed average was 2.75. In this particular case, you can see that the p-value is going to be quite small because I do not expect to see a difference of 2.75 over repeated sampling under this situation of no difference. Okay, a little bit about the theoretical considerations here. We don't actually use the sampling distribution computed from StatKey to do our testing. What we actually use is what's called the t-distribution. The t-distribution has a statistic here given on the bottom of page 5. And this quantity here looks a lot like a z-score, and it acts like a z-score. If this t quantity is large, say bigger than 2, then I'm going to have evidence that my data is an outlier against a no difference scenario. So it's against this distribution here, computed under no difference. If this t quantity is quite small, okay, that means you're within the realm of these other dots here. Quite small being, less than 2 or bigger than -2. So we could be on either side here. If t is positive, it just means you're above 0. Your average was above 0. If t was negative, that means your average was below 0. The t-distribution actually looks a lot like a normal distribution. Here's a couple of just quick schematics. One thing about the t-distribution is it requires the use of degrees of freedom, or that's what it's indexed by, is its degrees of freedom. And the degrees of freedom is just the number of observations minus 1. One thing about the theoretical approach is it requires that our data be normally distributed. And we know how to obtain a normal curve over the top of our histogram. We did that in the last handout. We also looked at a normal quantile plot in the last handout. So you can get these from the red drop-down menu. So over here in Jump, where I would get those is from my red drop-down menu here. Normal quantile plot. You can add a bell curve over the top of your histogram by continuous fit normal curve. So we covered those on the last handout. This data here, most of the points here fall between these bands. So I'm going to say that my data is in pretty good shape. It's not exactly bell curve, but it's close enough. So technically, for all the mathematics to work out, this assumption has to be true, exactly, or completely true. In practice, a little bit of skewness is not going to be a problem, but substantial skewness will be. And the big idea there is we just don't want to be using an average on skewed data. If the data is fairly symmetric, which this data is, then an average is going to be an okay measure to use. So that's the big picture there. All right, let's get into the test then. So the research question, is there a statistically significant difference on average between the two doctors? So the parameter that we're testing here is the average difference between the two doctors. We have a null and alternative hypothesis. The null is always built under the no difference scenario. In that case, we would have a mean equal to 0. So this is just the parameter. This here is what that would look like in words, I guess. We're going to use a 5% error rate in our test. To get the test, all I need to do is, from my drop-down menu, select Test Mean. So let me show you where that's at. From my drop-down menu here, select Test Mean. And the value that I want to put in here is indeed 0. 0 is the value that I want to be testing. This value that goes in this box is the value that's in the null hypothesis here, which is 0. Go ahead and say OK. And my output will be provided over here on the right side. So let's talk through that output quick. Here in the middle of the screen is just the computations of my test statistic. I would just take the average difference, which was 5.5. Excuse me, the average difference, which is 2.75. Subtract off what I would like to test, which is 0 again. That's the hypothesized value. And then divide by that standard error quantity that we talked about up above. So 2.75 minus 0, all divided by half, is 5.5. The output, the testing output, bottom of page 8 over here, we actually get 3 different p-values. So let me talk about those quickly. The top one is for the two-sided test. So the one that has bigger than the absolute t is for the two-sided test. Test number 2 here, that's greater than t, is for a one-sided right test. And less than t is going to be for a one-sided left test. It's been a while since we talked about two-sided, one-sided right, and one-sided left. But again, this is just determined by the research question or the inequality that you're putting in HA. Now, if this test statistic is bigger than 2 or less than -2, then it's going to be extreme or an outlier. And the test statistic here is 5.5. This little picture that JMP puts underneath this output is the same as what I was showing you up above here. It's that sampling distribution under the no difference scenario. Bottom of page 4. It's centered at 0. It looks like it kind of settles down there at about 1.5 or 1.75. And in this picture, 2.75, which is going to be way up here, is going to be extreme. That's what I have here in the next page. So this schematic right here is what JMP is showing you with that output. Now it's actually using the t-distribution instead of the simulated distribution, but that's what that is. And we can certainly see that's extreme. That 5.5 is just telling us that 2.75 is more than 5 standard deviations away from 0. So again, this test statistic here acts just like a z-score. This is just showing me how far away am I from 0 in terms of the standard error or in terms of the standard deviation of the averages. So this outcome here of 2.75 again is extreme. Okay, let's keep going. Obtain the p-value. Well, the one that I'm going to want to use is p-value number 1 here. This is a two-sided test. If I go back up here, I just want to know whether or not there's a difference. The research question is just asking, is there a difference? So it's two-sided. So my p-value here is going to be less than 0.0001. Is that less than 0.05? Yes, it is. So I do have enough evidence for the research question. So I get to say that we are 95% confident that there is a difference on average between these two doctors. All right, how about the next part? The 95% confidence interval. The 95% confidence interval is going to allow us to express or determine how much difference I have between the two doctors. So the hypothesis test just asked, is there a difference? The confidence interval is going to tell us how much of a difference I have between the two. When we use the confidence interval, or when we compute the confidence interval, we're actually going to use the first distribution that I showed you, the distribution that was not centered. So this here was the first distribution that we showed. It has an average of 2.75, and again, it has a standard error of 0.5. What a confidence interval does is just tries to capture the middle 95% of these observations over those repeated sampling. The computations are, you just simply take the average minus what we call the interval coefficient times the standard deviation of the averages. The upper limit is going to take the average plus that quantity. This quantity right here is the margin of error quantity. So IC times standard error, or IC times the standard deviation of the averages, is the margin of error. So the calculations for our example here, 2.75 is my average. That's what we start with. We subtract the interval coefficient, which that number is 2.04, which I'll show you that down below where we get that. And then the standard deviation is the standard error here of 0.50. Now this is not the standard deviation of the data. That would be 2.828. But this is the standard deviation in this picture, in those repeated averages, which is that 2.828 divided by the square root of 32. That's how we got that standard error mean. So standard error mean is the same thing as the standard deviation of the averages. So we do that math. The lower side I get about 1.73 and the upper side I get 3.77. So this is the 95% confidence interval here. So we are 95% certain that, on average, Dr. A will find between 1.73 and 3.77 more palpal lymph nodes than Dr. B. Now, Dr. A is finding more here because that's how the differences were computed. The differences were computed as Dr. A minus Dr. B. So if I have a positive difference, I have a difference bigger than 0, that means Dr. A is finding more. I've marked 0 here. 0 would indicate that there's no difference. This confidence interval clearly stays above 0, which means Dr. A is finding more than Dr. B. How much more is given by these endpoints. Okay, real quickly, how do I find the 2.04 number? There's an app that will allow us to do that. There's lots of different apps out there. This one is from the University of Iowa. What this app requires is that I put in the degrees of freedom, which is going to be n minus 1 here. It's 32 minus 1. I want to use the two-tailed here. So they're taking 2 times the probability of absolute x. That's the two-tailed. And I want to be 0.05 is going to be my level here. And what is returned here is the value 2.04. So from a t-distribution, I get the middle 95% when I stay between negative 2.04 and positive 2.04. Now this is off of the t-distribution. What I do when I calculate my confidence interval is just scale that up to the regular or to this distribution. So I need to multiply that by, again, my standard error deviation of the averages. And then I take that margin of error quantity and subtract it and add it to my average. Okay, some final thoughts quickly. The hypothesis test considered whether or not we could establish statistically significant differences between the two. That was the purpose of the test. The conclusion from this hypothesis test said that, yes, indeed, on average, there was a difference. The 95% confidence interval suggested that, on average, Dr. A would find about 2 to 4 more palpal lymph nodes than Dr. B. Okay, just a little bit of an aside here on page 11 and 12. One negative about considering the differences is that I actually lose track of the original values. So if I base my analysis on the differences, I can see that I have 3 here. That's the difference. But I really don't know what Dr. A's count was and what Dr. B's count was here. I mean, the analysis doesn't take that into consideration. I think the values here were 4 and 1, if I recall. But those values could have been 7 and 4. Or they could have been 120 and 117. So this test works with the differences, but it does in fact ignore the actual values here. If these values are 4 and 1, which they were, then being 3 off is quite a bit. But if these values were 120 and 117, being 3 off is not that big a deal. This test does not have the ability to distinguish between those two situations. One thing that we could do that keeps all the values in perspective is to consider a scatter plot. So that's what's on the next page here. So a scatter plot is going to allow me to look at both sets of measurements. I have Dr. A on the y-axis, on the x-axis, and Dr. B on the y-axis here. And I have placed the y equal x line down this plot. X line, is going to be where Dr. A equals Dr. B. You can see that I have 3 times right here, and right here where I have agreement between those, where I have agreement in the measurements between Dr. A and Dr. B. There's some additional questions here on page 12 that I'd like you to consider. Okay, that does it for Handout 10. Thank you.